Howdy. So last week we went through acid-base notes. I think there's a worksheet, a graded worksheet this week that's going to talk about those acid-base notes. So you may have to go back and look at them if you haven't at this point. This is the notes over pH, and you will. I'll have some problems to do in the extended learning part of this, but there will also be some problems next week for you to do for a grade. So if you're watching these, it should help out. Again, email if you got questions as we go. Okay, so here's we talked about with net ionic equations how I kind of fib about spectator ions, and potassium iodide in a lab could be sodium iodide because that potassium or sodium is a spectator, and so I told little lies along the way. This is another one of those that's borderline a little lie. What this says is that water conducts a little bit of electricity in solution. I've always talked about covalent things when you drop them in water don't have ions to separate into, and so they don't conduct electricity. So sugar doesn't conduct electricity. Water, however, does what we call self-ionization. Water, when you put it with other waters, about 2 out of every billion water molecules, one of them gives away a hydrogen and acts as an acid, and the other one accepts that hydrogen and acts as a base. And so 2 out of every billion water molecules turn into hydronium ions and hydroxide ions, or acidic particles and basic particles. We talk about water can act as an acid or a base, but water overall is neutral. Why is water neutral overall? Not because it doesn't have any acidic or basic particles, but because it has exactly the same amount of acidic and basic particles, is what this is showing. A gentleman a long time ago figured out what the concentration of those particles was in solution. And so when we see brackets, we're talking about molarity. So if you take the concentration of the acidic particles and multiply them by the concentration of the basic particles, he came up with what is called the ionization constant for water. That's your KW, constant for water, 1 times 10 to the negative 14th. We should recognize that 14 number when we look at the pH scale, and we say the pH scale goes from 0 to 14. That's where that 14 is coming from. And so this is going to get us to the pH problems and not very long. Okay? But water does conduct a little bit of electricity even in its purest form because it goes through that self-ionization. So here we go. Here's our first little problem. I'll show you the pretty work underneath this once I do it by hand for you. So this says find the hydroxide ion concentration of 3 times 10 to the negative second molar HCl. The key to victory here is to figure out whether HCl is an acid or a base in this thing. And what we have here is that HCl, when we drop it in solution, is a strong acid. So it's going to fully break into hydrogen ions and into chloride ions. Good. And so if I have 1 HCl, I get 1 hydrogen ion and 1 chloride ion. If I had 5 HCls, I would get 5 hydrogen ions and 5 chloride ions. If I had 3 times 10 to the negative second molarity of the HCl, then what that means is I'm going to break that thing into 3 times 10 to the negative second molar hydrogen ions floating around in solution. Good. And so what they're telling me with that hydrogen ion concentration, that is the hydrogen ion concentration, or we talked about this in the last video, the hydronium ion concentration. Excuse me. Woo! And so whatever they give you, if this is an acid, they're giving you the concentration of the acidic particles. And so when they say in this problem, find the hydroxide ion concentration, we are looking back at that formula we just saw on the last slide. So H3O, the acidic particles, times the basic particles will always equal this 1 times 10 to the negative 14th. I will say this number is at room temperature, so we're talking about 25 degrees Celsius. If it's not 25 degrees Celsius, that number would change. When are you going to see it not at 25 degrees Celsius? You're not. unless you take AP chemistry with me. And then it's just a simple problem of taking and plugging in that value for the H3O. So we have, again, generic equation with the numbers in it, 3 times 10 to the negative second, times the hydroxide ion concentration would equal 1 times 10 to the negative 14th. And then we can plug this guy right into the calculator. So hydroxide ion concentration, I'll plug it in so you can see 1 times 10 raised to the negative 14th divided by, in scientific notation, you're going to divide it in scientific notation, has to be in parentheses, 3 times 10 raised to the negative second, at least I hope. Close those parentheses out, and we get this number, 3.33 times 10 to the negative 13th. So our hydroxide is 3.3 times 10 to the negative 13th power. And that's it on that first question. Now it asks on some questions further along, is this thing acidic or basic? And so to figure out whether it's acidic or basic, we have to figure out whether we have more acidic particles or more basic particles. And in this case, we have, I don't know, more than 1 billion more hydronium ions than we do hydroxide ions. There's very few of this. This number is way smaller than the H3O, and so this thing would be acidic. So there's a snapshot if you need to pause it so you can look through the pretty work with nice handwriting. There it is. Now, these numbers are tough to deal with. People don't like these really tiny numbers. So what I did is I invented something called the pH scale. And so the pH scale, we should be comfortable with the idea that the pH scale is 0 to 14, where 7 is neutral. The closer you get to 0, the more acidic. The closer you get to 14, the more basic. It's a logarithmic scale, which means every point along the scale is increasing tenfold. So if you had something that was a pH of 2 and then something that was a pH of 4, we didn't double how much basicness there is. There's 100 times more basicness, because 2 to 3 is tenfold and 3 to 4 is another tenfold. Right? What else works along that logarithmic scale? Decibels, so the volume of things works along that scale. Some of your stereos at home read in decibels. The Richter scale is a great logarithmic scale. So if you have an earthquake that has a Richter scale reading of 4 and then an earthquake that has a Richter scale reading of 8, you didn't double the amount of shaking of the earth. You increased the shaking of the earth by 10,000 times. Because every point is a factor of 10. So that's the idea here. Don't get caught. Somewhere you'll see a multiple choice question in your life that says if you go from 8 to 10 on the pH scale, you get more basic. And then it'll say if you go from 2 to 4, do you get more or less acidic? You're getting less acidic because you're moving towards that pH of 14. Good? Good. So here's our second formula. There's 4 formulas we're going to use here. Here's our second one, is pH equals negative log of the hydronium ion concentration of the acidic particles. It's a nice way to take those awfully small numbers and put them into numbers that we can use from 0 to 14. Everybody can look and go, pH of 2, that's smaller than 4, so that's more acidic, and so it's easier that way. When I invented the pH scale, I was doing my professional ballet training in France, and so pH stands for pouvoir hydrogène. It's French for hydrogen power. That joke goes better in class. All right. Here's a little pH scale for you to glance at. I don't know if you can see it that well. It probably helps. It's just a real quick generic look at some stuff along the pH scale. So wine's acidic, coffee, sometimes people think coffee is bitter tasting, but coffee should be acidic. Water right at 7 is neutral. Milk, lactic acid, a little acidic. Blood, slightly basic. That's why it tastes bitter. That's messed up. But that's why it would taste bitter. All right. And so you can pause that too and glance at them. Nobody's ever going to ask you whether lemon juice is more or less acidic than vinegar. But there's a peek at the scale. So here's the other couple formulas. So we just saw this one on the last slide, pH equals negative log of hydronium. You can also measure the hydroxide power, the basic power, same exact formula, except pOH, you're dealing with a concentration of OH. And then this is the easy one, so when in doubt, I try to get to the easiest one as fast as I can. This is pH plus pOH equals 14. And so I use this one first if I have a choice. And all we got left is a couple problems. I don't know that I'm going to be able to work through a couple problems fast enough, but we're going to try here. This says, what is the pH of 0.050 molar HNO3? HNO3, acidic or basic? Think about it, good. It's acidic. It's nitric acid, right? And so this 0.05 molar HNO3, they are giving me the hydrogen ions. Concentration is 0.050. Hydrogen or hydronium, same thing. And so they're asking for what is the pH. So generic formula, pH equals negative log of the hydrogen or hydronium ions. And we are plugging and chugging. pH equals negative log of 0.050. And that will spit out for us what our pH is. Good? In Algebra 2, you're supposed to currently be going over logarithms. For us, it's a button on a calculator at this point. Don't forget your negative. Negative. Your log button over here is sitting there. Negative log. And then you can plug in your 0.050 and it spits out what our pH is for us of 1.30. And that's it on that one. Because the pH is less than 7, we know that this thing is acidic. That's it on that one. And the last one here says, what's the molarity of HBr in a solution that has a pOH of 9.6? So pOH equals 9.6. They want the concentration of the acid. Concentration of the acid is the concentration of the acidic particles. That's our question mark. Now, none of the formulas we have both of those things in there. So what we're going to have to do is take that pOH and turn it into pH first. So we have pH plus pOH equals 14. pH plus 9.6 equals 14. And so our pH there equals 4.4. At least I hope. Now that we have the pH and the H, and we're looking for the hydrogen ion concentration, we can come back and use our other formula. pH equals negative log of the H plus or the H3O plus. So 4.4 equals negative log of that hydrogen ion concentration. I got 1 minute to tell you how to do this on a calculator. Negative sign has to come over. This is negative 4.4 equals log of H plus. In order to do this on your calculator, you have to do second button on your calculator, then the log button on your calculator. And when you do that, it's going to open up 10 raised to, there's the logarithmic 10 factor, raised to the negative 4.4. And that will give you the H plus concentration, what you're after. And so, looks like this on the screen. Second log gives you 10 raised to the negative 4.4, and you should get 3.98 times 10 to the negative 5th. That should be our answer. And so that's our hydrogen ion concentration. There's a snapshot of it. So you can see what they did there. How do you get from here to here? Second button, then log button of a negative 4.4. See ya.